Hey guys, welcome back. In this video, we'll be trying to solve the problem of the day on Geeks for Geeks of 3rd November, that is safe states. All right. You will be given a directed graph with V vertices and a number of edges. So you will be having an array called edges. They contain UV pairs. So you have an edge from U to V. All right. You have to find all the safe states within this graph. Okay. Now I'll be explaining what safe states are. Let's move on to the whiteboard real quick. All right. So I'll be using these two examples itself. All right. Now let's first understand what safe states are. Okay. They can be one of two things. All right. They can either be a terminal node or a leaf node. Okay. Basically, nodes with no outgoing edges can be considered a safe state. All right. So if you look at the first example, you have node 0 and node 4, right? This the 0th and the 4th node. They have no outgoing edges. So they are classified as safe states. So you can just add 0 and 4. All right. Apart from that, any node from which you can reach a safe state can be considered a safe state as well. Okay. So like now I have 0 and 4 inside a safe state. Now let's start from 1. Okay. From 1, I have a path to 0. Now if I check, 0 is already inside my safe state, right? Since it's a leaf node. So 1 also becomes a safe state. All right. Let's move on to the second node. For node 2 as well, if I go forward, I can see that I can go to the third node from 2, but 3 is not inside my safe state. So I'll ignore that. I will move forward. From 3, I can go to 4. 4 is in my safe state. That means from 2, I can reach 4. So 2 is also a safe state of mine. All right. Similarly, from the third node as well, I can reach the fourth node. Fourth node is already there in my safe state. So node 3 is also a safe state. All right. And this is basically how you find safe states. Now I'll do the next example as well for you guys. In the next example, the only leaf node you find here is 0, right? So now 0 will directly be added into your safe state. Apart from that, let's start from 1. From 1, can you reach any of the safe states? Now, our safe state currently is only 0. So basically, from 1, can you reach 0? No, you can't. So we leave that. From node 2, can you reach 0? No. From the third node also, can you reach 0? You can't. So here, basically, 0 is your only safe state. All right, like this is what you should output. Now, this is basically how it works. All right, now I'll be explaining how we can get this done. All right, so let me erase this. I'll try to make this quick and brief so it's easy for all of you to understand. All right, yeah. Okay, so the way we'll be solving this is we'll be following a DFS approach. You can either do BFS or DFS. I'm just doing it the DFS way because I like DFS. All right. So first we'll be having a hash set. All right. We'll basically be having a set to store if nodes are a safe state or not. Okay. So any nodes which are a safe state, we'll be adding it inside H. As simple as that. All right. We'll also be having an adjacency matrix to basically understand or to basically find out the neighbors of each node. See, if it is in this particular format, like it's not all like organized in any way, right? So to search within this, it would take a lot more runtime as compared to just looking it up on the adjacency matrix. All right, so we'll be first having an adjacency matrix, all right, for every single node. So here you have 5 vertices, so you'll be having 0, then you'll be having 1, 2, 3, and 4. All right. So now we'll just be filling this in. Okay. Now this stands for 0, 1, 2, 3, 4. All right. So from 0, can we go to any other node? As you can see, like 0 is a leaf node. So from 0, you can't go anywhere else. So the adjacency list of 0 will just be 0 itself. I mean, it'll be empty, right? You can't go anywhere else. Let's see from 1. From 1, you can go to 0, 2, 3, and 4. So we'll just be adding all that inside our matrix. Okay, because we know that from 1, you can go to all these nodes. Let's think about 2. From 2, you can go to the third node. We'll be adding that inside 2. From 3, you can go to 4. We'll also be adding that. From 4, you can't go anywhere else because 4 is a leaf node. So this will again be empty. All right. So this is our adjacency matrix. All right. So now what we'll be doing is we'll be doing DFS on every single node and finding out if it's safe or not. Okay. So we'll start from 0. Okay. From 0, we will check if DFS of 0 is safe or not. Now we know that 0 has no neighbors of any sort. So we can directly add 0 inside of hash set, meaning that 0 is safe. Okay. Now we'll move on to 1. We'll do DFS of 1. All right. DFS of 1 we'll do. And we have no information of 1 as of now. Right. So we won't put 1 inside a hash set as of now. We'll just be putting like 1 false or something, right? Like, we'll just make sure that one's thing is false, all right? And this is a hash set, so we have to give a value for everything as well. All right, anyways, now 1 will be false now. So we'll do DFS of 1. When we do DFS of 1, we reach 0. We see that 0 is already true inside our hash set, meaning that 0 is indeed a safe state. And since 1 goes to 0, 1 is also a safe state. So I can just change this false to true. Okay. And if you guys are still wondering as to how I find the neighbors, I find the neighbors from this adjacency list. All right. So from 1, the first neighbor is 0. So I explore that first and I just move forward. Similarly, we'll be doing that for every single node, and we'll be adding all the safe states inside this hash set. Then we'll just return this hash set as answer. All right, as simple as that. That's how this works. Let's try to code this out. Okay, so let's try and code this out. The first thing, as I said, you'll be having an adjacency matrix, right? So for every single vertex, we'll first be initializing an empty array, right? Then we'll be doing for u comma v in edges, right? Adjacency of u dot append v. So in this way, we can very easily create the adjacency matrix as required. All right. Now let's create a safe state. So it'll be a hash set like this. Now we'll create a DFS function. All right. So now the first thing what we check, if I in safe, then we can just return safe of I, basically meaning that our current state is safe, right? So now we don't need to look forward. However, if it's not, we'll just be initializing it as false for now. Okay, so like for now it will be false. Then we'll be exploring every single one of their neighbors. So for neighbor in adjacency matrix of I. So we'll check all the neighbors of our node I what we have right now. All right. If not DFS of neighbor, basically if it comes out that it's not reaching a safe state, we can immediately just return false. All right. Put this in caps. All right. If not, if the for loop completely executes and if it ends up reaching a safe state, I can just put safe of I is equal to true. Then at the end, I can just return the safe state itself. Right. That's how this works. Sorry, I don't have to return the safe state. I mean, I can return, like it's up to you. You can either return a Boolean value or you can give out the state as it is. All right. I don't think it really matters. Like, we'll check if we come across any errors. All right. Over here, answer will be equal to empty list. Now, all our safe states will go inside this. All right. So for I in range, we'll go through V. If DFS of I, basically if it's successful, then what will we be doing? We'll just be doing answer.append of I. That's basically it. All right. Let's see if this works. If this does not work, we can change this. Let's look at the error. 950. I'm not returning anything. Oops. Return answer. Yeah, it should work now. Okay, it ends up working. Let's submit. And there you go. It works. That's how you solve this problem. If you have any doubts, do let me know in the comment section down below. And that's all for this video, and I'll see you in the next one. Goodbye.